In today's video and class, we are going to look at chromatography as a separation technique. We start our introduction by looking at what chromatography is. So chromatography is an analytical technique that involves the use of a stationary phase and a mobile phase to separate a mixture into its component. And this technique separates molecules on basis of their differences in size, differences in shape, in mass, in charge, in solubility, and adsorption properties. The types of chromatography. So we have the paper chromatography, the thin layer chromatography, column chromatography, liquid chromatography, ion exchange chromatography, and affinity chromatography. And all these types of chromatography involves interaction between three components. 1. The mixture to be separated. 2. The stationary phase, which may either be a solid or a liquid. And 3. The mobile phase, which may either be a liquid or gas. Now look at the RF value. So when we talk of the RF value, or the retention factor value in chromatography, is a measure of the movement of substance along the chromatogram. And when we talk of the chromatogram, is the obtained result in a chromatographic process as shown in this diagram over here. The RF value mathematically is calculated by dividing the distance traveled by the component by the distance traveled by the solvent front. And the solvent front is the distance the mobile phase or the solvent travels through the stationary phase to separate the various components of a mixture. So from this diagram over here, we can say that this is the distance traveled by our compound, which is given as A over here, and this is the solvent front, also shown or given as B over here. The RF value is useful because the same substance under exactly the same conditions always give the same RF value. So this value can be used to identify an unknown substance. And in calculating or measuring the RF value in chromatography, there are some key points that we have to note. So one is that measurement is made to the middle of the separated compound on the stationary phase. So from this chromatogram, this is our separated component over here. So if you want to measure the distance traveled by this component on the stationary phase, we measure the distance from the baseline or the spotting line to the middle of the separated component over here as shown in the chromatogram, and this is given as A over here. So 2, RF value is usually expressed as 2 place decimals and has no unit. So example, so we can say that the RF of glycine in phenol is given at 0.49, and the RF values may be found sometimes expressed as percentages to avoid the use of decimals. And this can be done by just multiplying the decimals by 100. So example, the RF value for glycine in percentage in phenol will be given at the 0.49 times 100. So now looking at this chromatogram over here, if you want to calculate for the RF value for our compound over here, we will use the equation which is given as the RF value to be equal to distance traveled by the component on the stationary phase, and this is given as A over here divided by the distance traveled by the solvent or the solvent front, which is also given as B over here. So mathematically we can express the equation for calculating the RF value for the separated compound on the chromatogram here by saying RF is equal to what? A divided by B, where A happens to be the distance traveled by the component on the stationary phase and B happens to be the solvent front. Now let's try to do some calculations for the examples over here. So we have two examples. This is the first example, and this is also the second example. Now, so from the first chromatogram, which we are using as our first example, we can see that the distance traveled by our compound on the stationary phase is giving us 2.1 centimeters, and that of the solvent front is giving us 2.8 centimeters. So to calculate the RF value for this compound over here, so we will have 2.1 divided by 2.8, which is equal to 0.75. So for the second example over here, we have various compounds being separated. So we have compound A, compound B, C, and M. And also our solvent front over here happens to be 4.7 centimeters. So if we want to calculate the RF value for our separated compound A, we will have 0.7 centimeters divided by 4.7, and this is equal to 0.15. For compound B, the distance traveled by the compound is 4.1 centimeters. So the RF value will be 4.1 centimeters divided by 4.7, which is the solvent front, and this will be equal to 0.87. So for compound C, the distance traveled by the compound is 1.8 centimeters, and the solvent front is 4.7. So the RF value will be giving us 1.8 centimeters divided by 4.7 centimeters, and this is equal to 0.38 over here. So now let us look at some factors affecting RF value. So the RF value of a component in chromatography can be affected by several factors, like 1, the type of stationary phase, 2, the polarity of the solvent, 3, the polarity of the compound, and 4, temperature. Let's look at how solvent polarity affects the RF value in chromatography. So I'll explain how solvent polarity affects RF value in chromatography by using the chromatograms below. This is the first chromatogram, the second chromatogram, the third chromatogram, the fourth chromatogram, and the fifth chromatogram. So the chromatograms here shows result for thin layer chromatography using the same test sample, the same stationary phase, and the same mobile phase, but with different polarities. So we can see in the first chromatography that a mixture of 5% ethyl acetate and 95% hexane was used as the mobile phase. In the second chromatography, a mixture of 10% ethyl acetate and 90% hexane was used as the mobile phase. In the third chromatography, a mixture of 20% ethyl acetate and 80% hexane was used. In the fourth chromatographic, 100% ethyl acetate, which is a polar solvent, was used as the mobile phase. And in the fifth chromatography, 100% hexane, which is a non-polar solvent, was used as the mobile phase. So now if you are to compare the polarity of the solvent mixtures used as mobile phase in each of the thin layer chromatography, it can be seen that the solvent used as mobile phase in the first chromatography will be considered a less polar solvent to the second solvent mixture used as a mobile phase in the second chromatography. Also, the solvent mixture used in the third chromatography will be considered a more polar solvent than the one used in the second chromatography. The 100% ethyl acetate, which is a polar solvent used as a mobile phase in the fourth chromatography, will be considered the most polar solvent, and the 100% hexane, which is a non-polar solvent used as the mobile phase in the fifth chromatography, will be considered as the most non-polar solvent. And one key thing that we have to note is that the polarity of the solvent varied as a result of the different ratios of the ethyl acetate, which is a polar solvent, and hexane, which is a non-polar solvent used. So the higher the percentage of the ethyl acetate in the mobile phase, the more polar the solvent will be. But in terms of solvent polarity with a polar stationary phase, such as silica gel or aluminum or cellulose fibers, the most polar solvent will have the most affinity for the polar stationary phase and will travel the farthest with the separated compounds to provide a higher RF value as shown in the fourth chromatography, whilst the most nonpolar solvent will have the least or no affinity for the stationary phase, and in most cases will not be able to carry the compounds in the mixture through the stationary phase, which is polar, and this often result in a lower RF value, or in some cases an RF value of 0 if the compound to be separated is a more polar compound, as shown in the fifth chromatography. So in summary, the second and third solvent mixture, so which is 10% ethyl acetate and 90% hexane, and 20% ethyl acetate and 80% hexane, will be recommended as the appropriate mobile phase to be used in a chromatographic techniques, which usually involve a polar stationary phase. Let's see how the compound polarity affects RF value in chromatography. So assuming we want to separate two compounds, compound A and compound B, in a mixture by thin layer chromatography or paper chromatography, with compound A being the more polar compound and compound B the less polar compound, and using thin layer chromatography with the TLC plate. So this is the TLC plate over here, coated with silica gel as the stationary phase, and a mixture of 10% ethyl acetate and 90% hexane as the mobile phase. If the mixture is spotted onto the baseline, as shown over here on the TLC plate, compound A, which is a more polar compound, will have a strong affinity for the stationary phase and will be adsorbed most onto the stationary phase. And as this happens, the compound A will travel the least with the mobile phase and have the lower RF value as compared to the compound B, because of compound A strong affinity for the stationary phase. On the other hand, the compound B, which is less polar than compound A, will have a less affinity for the stationary phase but a strong affinity for the mobile phase. Hence, will travel at a faster rate with the mobile phase through the stationary phase to result in a higher RF value as compared to compound A. So as you can see over here, this is compound B with a higher RF value because of its strong affinity for the mobile phase and a less affinity for the stationary phase. And this is also compound A with a lower RF value because of a strong affinity for the stationary phase and a less affinity for the mobile phase. Let's now see how the stationary phase affects the RF value in chromatography. So first of all, the stationary phase significantly affects the RF value by determining how strongly a compound interacts with it. So example, a more polar stationary phase will result in a lower RF value for polar compounds because these compounds will travel less distance on the chromatography plate as they are more attracted to the stationary phase, whilst a less polar stationary phase will allow these polar compounds to travel further, giving them a higher RF values. So now let us look at these pictures and study them. So the pictures here shows two chromatograms in a thin layer chromatography with both using the same mobile phase. So these are the mobile phase that are being used, and with other required conditions but different stationary phase. The first chromatogram here uses TLC plate coated with silica gel, which is a less polar stationary phase than alumina. And the second chromatogram over here uses the TLC plate coated with alumina, which is more polar than silica gel as the stationary phase. So from these two chromatograms, it can be seen that the first chromatogram using the TLC plate coated with silica gel as the stationary phase has two separated compounds with higher RF values than the second chromatogram using the TLC plate coated with alumina as the stationary phase. And this is because the alumina acts as a more polar stationary phase than the silica gel. Hence, it's important to consider the polarity of the compound you want to separate, because a polar stationary phase will best separate polar compounds, whilst a non-polar stationary phase will best separate a non-polar compound. So hence, by selecting the appropriate stationary phase, we can optimize the separation of different compounds in a mixture based on their polarity and interactions with the stationary phase. Let's see how temperature affects the RF value in chromatography. So first of all, temperature affects the RF value by altering the solubility of the analyte in the solvent, as this causes the compound to move faster or slower up the chromatographic plate to result in a higher or lower RF value. And also, higher temperatures lead to slightly higher RF value, as the solvent molecules have more energy and can better dissolve the analyte molecules, allowing them to travel further up the plate. And to ensure a more accurate RF values, it's always important to maintain a consistent temperature throughout the chromatography process. So this is just a question for you to try your hands on. So what primary way does temperature affect RF value? Let's look at the RS value in chromatography. So first of all, what I want us to note is that in some chromatographic cases, it is only possible to obtain a good separation in a long run where the solvent is allowed to run off the paper or the TLC plate. And in this case, RF values cannot be measured. Instead, a reference standard is included as one of the samples and the test compound distance compared with the distance moved by this known substance. Example, in the chromatography of sugars, glucose can be used as a reference standard. And from the chromatogram shown here, glucose was used as a reference standard and ran alongside with the sugars, lactose and galactose in a chromatographic process. So if you want to calculate the RS value for our lactose, it will be the distance traveled by the lactose from the baseline or the origin over here, which is given as A, divided by the distance traveled by our reference standard, which is the glucose, from the baseline or the origin, given as C over here. And mathematically, this can be written as RS value to be equal to A, which is the distance traveled by our sample, which is the lactose, divided by C, which is the distance traveled by our reference standard on the chromatogram. But in general, the RS value mathematically can be expressed as distance compound has moved from origin or the baseline divided by the distance the reference standard has moved from the origin or the baseline. So in summary, RS values represent the ratio of the distance traveled by a compound to the distance traveled by a reference standard. And also, the RS value can be used in place of the RF value if one, you want to compare the migration distance of a substance to a reference standard in chromatography, as shown in the chromatogram over here. And two, if the solvent front runs off the stationary phase, making it difficult to calculate the RF value accurately. So let's see some key points about RF and RS value. So we'll start with the RF value. 1. RF value cannot be greater than 1. And the RF value is a general measure of how far a compound travels relative to the solvent front in chromatography. And the RF value is calculated as RF to be equal to distance traveled by compound divided by the distance traveled by solvent front. And if the RF value is 1, then it means that the compound to be separated has no affinity for the stationary phase, but travels with the solvent front. Or in other words, the compound has a strong affinity for the mobile phase. And if the RF value is 0, then it means that the compound has a strong affinity for the stationary phase and has no affinity for the mobile phase. So now let's look at the RS value. The RS value can be greater than 1, and it's a more specific comparison of the distance traveled by a compound to a reference standard in chromatography. And it is calculated as RH to be equal to distance traveled by compound divided by the distance traveled by the reference standard. The basic principles involved in the separation process in chromatography. Example, in the separation process of plant extract in paper chromatography. So first of all, chromatography is a separation technique that takes advantage of the different pigment solubilities and relative affinities for the stationary phase used. And all chromatography works by having a mobile phase and a stationary phase, which allow for separation of the different fractions of the original mixture. And when we talk of the mobile phase, is the liquid or gas that carries the mixture to be separated through the system containing the stationary phase. So in liquid chromatography, the mobile phase is liquid, and in gas chromatography, the mobile phase is gas. The stationary phase is the substance that stays fixed in the column or chromatographic tank through which the mobile phase travels through. And the fraction is the component of the original mixture. Again, chromatography works because of the different affinities. And this is how strong a substance is attracted to another substance of the various components of the mixture towards the stationary and the mobile phases, which are dictated by two properties of the molecules. One, adsorption, and two, solubility. And these different affinities allow for the separation of the components in a mixture. So we can define adsorption as the property of how well a component of the mixture sticks to the stationary phase, and the solubility as the property of how well a component of the mixture dissolves in the mobile phase. So now let us use this chromatogram in our paper chromatography as an example. So from the chromatogram here, this plant pigment, which is likely to be our chlorophyll B, and absorbs the most onto the stationary phase, while this plant pigment, which is likely to be carotene, dissolves the most or dissolves best in the mobile phase. So the pigment that absorbs the most onto the stationary phase will have the lower RF value, and the pigment that dissolves the most or dissolves best in the mobile phase will have the higher RF value, as shown in the chromatogram over here. So from principle, the higher the adsorption of a molecule or compound to the stationary phase, the slower the molecule or compound will move through the stationary phase. And the higher the solubility in the mobile phase, the faster the molecule or compound will move through the stationary phase. So using the chromatogram over here as an example, we can see that the most adsorbed plant pigment onto the stationary phase is chlorophyll B, followed by chlorophyll A and xanthophyll. And the most dissolved plant pigment in the mobile phase is the carotene. And in terms of RF value, which is defined as the distance traveled by the component over the distance traveled by the solvent or the mobile phase, or the measure of how far a molecule travels in chromatography compared to the mobile phase, we can see that the most adsorbed plant pigment onto the stationary phase will have the smallest RF value, and the most dissolved or the most soluble plant pigment in the mobile phase will have the highest RF value, as shown in the chromatogram here. So let's now look at the recovery of compounds, example our plant pigment, from our cellulose filter paper after chromatography. So what we have to note is that plant pigments can be eluted or recovered from the paper after chromatography by cutting the pigment spots from the chromatogram and placing it in a test tube containing a small volume of a suitable solvent. So what it means is that if I want to recover this pigment over here from my paper, I'll just cut this pigment spot over here and put it in a test tube containing a suitable solvent to elute the pigment. If I also want to recover this plant pigment over here, I'll just cut the pigment spot over here and put it in a test tube containing a suitable solvent. And again, if I want to recover this plant pigment, I'll just cut this pigment spot over here and put it in a test tube containing a suitable solvent. So this is how we can recover our plant pigments after running our chromatography.